On October 3rd, 2025, the interstellar object 3I/Atlas made a remarkably close approach to Mars, passing at a distance of just 0.2 astronomical units. Numerous telescopes were set to capture the event, yet the only public evidence came from a faint signal noticed in nighttime images taken by Perseverance, independently identified by two experts. Although NASA, ESA, China, and the UAE had promised updates from their Mars orbiters, no official data was ever released. This extraordinary event, the most significant since Oumuamua, remains uncertain. Was it truly an interstellar comet, or did we miss a rare chance to study one up close? The implications for future space research and our readiness to respond are immense. On that October day, 3I/Atlas passed about 29 million kilometers from Mars, a small gap in cosmic terms, offering an unprecedented opportunity for scientific observation. It marked the first time an object from another star system came so near a planet while multiple spacecraft were poised to observe it. The Mars Reconnaissance Orbiter, Europe's Mars Express, the UAE's Hope Probe, and China's Tianwen-1 each received urgent observation requests. Their teams quickly adjusted mission schedules, recalculated the object's trajectory, and prepared to capture rare images of this traveler from beyond our solar system as it swept past the red planet. This opportunity was brief. At its closest point, Comet 1/Atlas raced across the Martian sky far faster than a typical comet, making observation extremely challenging. Scientists had only a few days to capture it before it vanished into the sun's glare. For planetary researchers, the objective was straightforward: obtain clear images from orbit that could reveal the structure of the surrounding cloud and perhaps show fragments breaking away. If the comet's core began to disintegrate, specialized instruments might detect the distinct spectral fingerprints that distinguish distant interstellar ice from the familiar ice found in our solar system. Every available resource, from Mars rovers to orbiting spacecraft, was pushed to its limit. The goal was simple: a single sharp image or reliable reading could reveal where the comet came from, what it's composed of, and how material from other star systems is formed. At stake was the chance to examine a pristine fragment of interstellar matter, to test long-standing theories about planetary creation, and to gain direct insight into an object that began its journey light years away. As the spacecraft focused on the passing visitor, excitement spread among scientists and the public alike, all hoping that this fleeting encounter would yield meaningful data and perhaps a glimpse of something truly new. The Perseverance rover's camera captured only a faint, blurry glow in the Martian night, the sole trace of Comet I/Atlas after its close approach to Mars. The discovery was made and shared by Stephen Burns, a geologist and skilled amateur analyst, together with Simon Stimthorn, known for his precise work with planetary imagery. Both researchers downloaded the raw images directly from NASA's public archive soon after they were released. Their technique was simple in concept but demanding in practice. They stacked multiple long exposure frames, aligned them with background stars, and carefully filtered out noise until a dim point of light emerged exactly where the comet was predicted to appear. The result wasn't a striking photograph, but a meticulously processed and labeled image shared online. It revealed a small, hazy dot surrounded by a faint glow, the spot matching the expected path of 3I/Atlas. There was no sudden brightening or unusual activity, only the quiet confirmation that the object had passed within view of Perseverance's camera. Burns and Stimthorn released their findings with caution, noting that the signal was extremely weak and lacked visible structure. They posted the annotated images on X and Blue Sky, clearly marking the comet's position and explaining their image processing steps so others could verify the observation for themselves. In planetary science, discoveries like this matter. They prove that even when official information is limited, careful examination of publicly available data can still reveal something new. The small, faint dot seen in Perseverance's image remains the only ground-based evidence that Comet 3I/Atlas truly passed by. It wasn't a major triumph or a disappointment, but it demonstrated what curiosity and persistence can achieve when people make full use of open data. The process of confirming the faint trace of 3I/Atlas began with raw images from Perseverance's Mastcam Z camera. Each exposure lasted 29 seconds during the Martian night. On October 3rd, the rover captured 36 images, and on October 4th, another 40. Researchers downloaded the originals from NASA's archives, pairing each with a corresponding dark frame to remove sensor noise. They then applied calibration files to correct for camera sensitivity and dust on the lens. Aligning the images was the next crucial step, every star field in the photos was compared to predicted sky maps centered on Mars, compensating for the rover's position and the slow drift of the Martian sky. Tiny adjustments ensured even the faintest stars lined up perfectly across all frames. Problematic pixels and distortions were removed using methods like outlier rejection and median filtering, which eliminated cosmic ray strikes and random noise, while any remaining flaws were gently corrected to produce a clean, consistent image. Once the cleaned and aligned images were ready, the researchers combined them using both median and average stacking to produce the strongest possible signal. They subtracted the calculated background sky brightness, which revealed extremely faint objects that were otherwise invisible. The final composite showed a dim, slightly blurred point of light exactly where 3I/Atlas was expected to appear, matching the predicted position from before the flyby within acceptable error margins. The brightness of the signal was measured and confirmed to be significantly higher than the background noise, passing the standard signal-to-noise test. The detection was verified again using publicly available software, and every step of the process, including settings and methods, was shared so others could reproduce the results. This created a transparent and repeatable approach that minimized the risk of mistaking random noise for a true detection. Still, rumors spread faster than the verified data. As soon as faint signals from Perseverance's Mastchem Z appeared, people began claiming they could see brighter streaks or shapes in images from other Mars rovers. One widely circulated picture, showing a faint streak from a Perseverance frame taken on October 3rd, was quickly interpreted by some as direct evidence of an interstellar object visible without special instruments. Online discussions filled with marked up versions of the photo and speculative explanations. However, careful checks told a different story. Emily, a respected planetary geologist known for her precise positional analyses, verified the coordinates using JPL data and confirmed that the claimed bright streak did not align with the comet's expected path. The path and timing of the line matched perfectly with Phobos, Mars's innermost moon. Its motion, direction, and elongated appearance were exactly what would be expected from Phobos moving across the sky during a long exposure. The conclusion came quickly. The bright line that had drawn so much attention wasn't an interstellar object at all, but a familiar moon caught mid-motion. Another moment of excitement came from an image taken by Mastchem Z on October 2nd, which showed a sharp, fast streak that puzzled many observers. Space enthusiasts compared its movement to the predicted path of Comet 3I/Atlas. However, the streak crossed the frame in less than a second, far quicker than the comet was expected to travel across the sky. Its brightness and motion suggested it was something nearby, or possibly a camera artifact, not a distant comet tens of millions of kilometers away. Experts like Emily shared detailed comparisons showing how much faster and differently the streak moved compared to 3I/Atlas's predicted path. Most observers agreed with this analysis and returned their focus to the faint, verified signal seen in the confirmed data. The incident became a valuable reminder. In space research, every streak of light must be tested carefully, checked against predictions, measured for speed, and examined for camera effects before drawing conclusions. The tools to do this are open to everyone. The process is transparent, and the scientific community can quickly identify errors. Meanwhile, Mars orbiters were ready and waiting. The Mars Reconnaissance Orbiter, equipped with its high-resolution camera, held the potential to capture the clearest images ever taken of an object from another star system, all from the surface of another world. Because its camera could only cover a small section of the sky and was extremely sensitive, getting a clear image relied entirely on perfect timing and precise targeting. ESA's Mars Express spacecraft, equipped with specialized cameras and the Omega instrument, had a different advantage. It could scan wider regions and detect gases and chemicals in the clouds surrounding the comet. The Trace Gas Orbiter, with its Nomad and Cassis instruments, was also prepared to take both visual images and detailed light readings. Their shared objective was to uncover chemical clues that could distinguish Comet 3I/Atlas from other comets nearby. The UAE's Hope probe and China's Tianwen-1 mission added broader coverage, observing from wide angles and potentially capturing more light data. Together, these orbiters offered the most promising technology available. Positioned around Mars, they had the best vantage point to study the comet at its closest approach, something no Earth-based telescope could achieve due to the sun's glare. In theory, the high-rise camera could map the comet's shape or even detect fragments if it was breaking apart. Omega and Nomad, designed to identify trace gases, might detect unusual molecules or rare atomic signatures, offering the best chance to determine what the comet was made of. Each instrument team fine-tuned their settings to capture the clearest signals possible, weighing exposure time, data compression, and the risk of missing the comet or overwhelming their sensors. So far, no original images have been released. As of October 7th, no detailed data or photos from any Mars orbiter have been made public. Routine updates, press statements, and even basic previews remain either delayed or withheld, mainly due to data processing backlogs, strict release policies, and the timing of a government shutdown that coincided with the event. The world is waiting, knowing that vital data might already exist but remains held up in review. Pointing a spacecraft toward a fast-moving target millions of kilometers away requires balancing precision with risk. The predicted position of 3I/Atlas in the Martian sky was constantly refined as new tracking information improved the accuracy of its path. Every mission relied on these shifting predictions to plan when and where to take their images, but the process wasn't automatic. Orbiters such as Mars Reconnaissance Orbiter and Mars Express had to adjust their orientation, sometimes turning several degrees away from normal observation targets, without knowing for certain if they were aiming at the right spot. Instrument teams set exposure times and camera settings with no real-time confirmation, making every image an act of calculated guesswork. Point, capture, and hope the comet was in view. Communicating through deep space networks added another layer of uncertainty, since every transmission from Mars must be carefully scheduled. Science data, operational updates, and essential commands all share limited communication time, forcing difficult choices about what to send first. Even when everything went perfectly, the resulting images could remain stored on board for days or weeks, waiting in a queue behind higher priority data or delayed due to ground station availability. A small error in timing or orientation could mean the difference between a groundbreaking discovery and a blank frame. In reality, there's no live tracking, no chance to redo a missed shot, and no confirmation until the data finally makes its long journey back to Earth. These challenges aren't the result of poor planning or faulty equipment. They're simply the realities of operating in deep space, where every observation involves uncertainty. You make your best estimate, point the camera, and wait for the data to return. The fine line between capturing something and missing it entirely is part of how space exploration works. For 3I/Atlas, the waiting isn't due to secrecy, but to the sheer difficulty of photographing something in the vastness of space. The sun's position creates an unavoidable obstacle. As October progresses, Comet 3I/Atlas moves closer to passing behind the sun from Earth's point of view, reaching that position around October 21st and 22nd. By the second week of October, it becomes too close to the sun's glare for any telescope to observe safely. This isn't a matter of choice, it's dictated by orbital mechanics. From mid-October through early December, most Earth-based and even many space-based telescopes are unable to see it. The comet's closest approach to the sun occurs on October 29th and 30th, right during this period of blinding sunlight. Ironically, the moment when it's most likely to change or fragment is exactly when it's hidden from view. The lack of updates from Mars orbiter teams isn't about withholding information, it's about following strict procedures. The engineers and imaging specialists at JPL have to review every frame for radiation hits, reflections, and tracking errors that become more serious when imaging something small and fast moving. The normal techniques used for steady scenes on Mars don't work when the target is flying past at high speed. Even a tiny error in aligning frames or missing a single artifact can create misleading results, showing something that isn't real or erasing what actually is. So the decision becomes clear: release an unverified image and risk fueling another wave of speculation, or wait for thorough verification and face criticism for being too slow. Delays within multiple organizations, postponed verification steps, and even the temporary government shutdown have all added layers of complication to an already difficult situation. At this point, no one is holding back information. Everyone is simply waiting for dependable proof to emerge. The next clear photograph or signal must be one that speaks for itself, free of uncertainty and interpretation. Despite all the confusion, the working hypothesis remains intact. Scientists still believe that 3I/Atlas is most likely an interstellar comet, an ordinary traveler from another star system composed mainly of frozen carbon dioxide and lacking the dicarbon that gives typical typical solar system comets their familiar greenish color. Early analyses hinted at an unusual mixture of volatile materials and possibly an excess of heavy metals, particularly nickel, as seen in some spectra. However, these are still preliminary suggestions, not confirmed results. No verified chemical breakdown has yet been published by any observatory or research group. The definitive answer will only come from a combination of consistent instrumental readings and carefully tracked changes over time, data that can conclusively prove or disprove whether 3I/Atlas truly behaves like a conventional comet based on its molecular composition and light emissions. For now, with Earth's telescopes unable to make direct observations until December, attention has shifted toward the few instruments still capable of monitoring space from better vantage points. The LASCO C3 camera aboard the SOHO spacecraft continues to scan near the sun's glare through the end of November. Its sensitivity is limited. It can detect objects no fainter than magnitude 8 or 9, so it will only capture 3I/Atlas if the comet brightens dramatically. Even then, detection would depend on both luck and timing. Meanwhile, ESA's JUICE mission, currently coasting outward from Jupiter's orbit, may have a brief observation window in early November. If its instruments are oriented correctly and the comet remains luminous enough, it might succeed in capturing a few distant frames. Still, there are no promises, no confirmed plans, and no official release schedule for any images that might result. Beyond these possibilities, no other missions or ground-based efforts are planned for that period, leaving scientists and enthusiasts alike waiting for the next reliable glimpse of this mysterious interstellar visitor. Keep a close watch for SOHO C3 imagery captured between the last days of October and the end of November, since new observations might appear during that period. Also, make a habit of visiting the ESA and JUICE mission websites in early November, as they could release updates or official statements then. As November draws to a close and December begins, Earth-based telescopes will once again have the opportunity to spot the comet. Large observatories and skilled amateur astronomers are already preparing their instruments, waiting for the chance to detect it if it shines brightly enough to pierce the background of the night sky. However, no claim will be accepted without firm, measurable proof. Only concrete evidence from scientific instruments, like unmistakable light signatures, distinct and verifiable photographs, or a pattern of changes recorded over time, will be convincing enough to confirm its existence. This time, caution guides every observation. We've been reminded that without a wider network of space-based telescopes, it's easy to miss a fleeting visitor from another star system, hidden just beyond the range of our current vision. Up to this point, the only public image is a faint composite frame taken by Perseverance's Mastcam Z, enhanced and shared by independent enthusiasts who aren't part of the official project. Detailed color imagery or surface analysis from Mars orbiters hasn't been published yet. With the sun currently obscuring our view from Earth, NASA, ESA, and other space agencies have delayed releasing new findings. That means key information about the object's composition, its reflective properties, and its physical structure remains incomplete until clearer images or spectral charts become available, either from the JUICE spacecraft or once Earth regains its vantage point of Mars in December. All we have is that one dim signal as the basis for speculation. For now, the question of what truly makes the 3/Atlas object unique continues to hang unanswered, wrapped in uncertainty and waiting for the next glimpse that might finally reveal the truth.